Hi everyone, and welcome to part 4 of our RCM case study. Today we have a very exciting topic to explore, condition-based maintenance. Let's get right into it. Condition-based maintenance, or CBM, is also referred to as on-condition maintenance. These two terms are used synonymously. A condition-based maintenance task is performed at a defined interval to detect a potential failure condition so that maintenance can be performed before the failure occurs. Most failure modes give us a warning that failure is in the process of occurring. In other words, there's evidence of impending failure. Examples of potential failure conditions are illuminated warning lights, increased temperature, increased vibration, noise, heat, and wear. In the context of reliability-centered maintenance, these are called potential failure conditions. Potential failure conditions can be detected by using relatively simple techniques such as monitoring gauges, measuring brake linings, or feeling for vibration via human senses, employing more technically involved techniques such as thermography, frequency analysis, oil analysis, or thermal imaging, and continuous monitoring with devices installed directly on machinery, like strain gauges and accelerometers. In order to determine if a condition-based maintenance task is technically feasible, potential failure conditions must be evaluated. To do so, let's take a look at the P2F curve. The x-axis is time, which can be measured in any units such as calendar time, operating hours, miles, cycles, takeoff and landings. The y-axis is the resistance to failure. The time that a new component is installed is depicted at the top of the y-axis, indicating the maximum amount of resistance to failure. As most components remain in service, the resistance to failure declines, and eventually signs of impending failure are exhibited. In other words, potential failure conditions develop. A potential failure condition is represented by P. If the potential failure condition goes undetected and we don't intervene, eventually failure occurs. Failure is represented on the P2F curve as F. The P2F interval is how long we have from when the potential failure condition is detectable to the point that failure occurs. The P2F curve is incredibly valuable because on-condition task intervals are determined based upon it. Let's look at an example for the failure mode V-belt wears due to normal use. Let's assume a new V-belt is installed. This is illustrated at the top of the y-axis where resistance to failure is at its maximum. Failure would be belt breaks. But before a V-belt breaks, it develops a potential failure condition. That is, it develops visual evidence of impending failure such as cracks and frays. Let's say our RCM working group reports that the P2F interval is 6 months. That is, from the time that visual evidence of wear on the belt is detectable to the point that the belt breaks is 6 months. So that means that we have to inspect the belt at intervals less than 6 months to ensure that we don't miss the potential failure condition. Let's assume the RCM working group decides to inspect the V-belt every 3 months, and let's see how this plays out. A note to make about on-condition maintenance is that every time the belt is inspected, you won't necessarily find the potential failure condition. So let's assume on this occasion the belt is inspected just before visual evidence of wear on the V-belt is detectable. So during the time between the next inspection, visual evidence of wear develops. However, the wear isn't discovered until the next inspection, which is 3 months later. That means that there's a minimum of 3 months remaining before the belt breaks. In the context of RCM, this is referred to as the net P2F interval. The net P2F interval is the minimum amount of time you have left to take action once the potential failure condition is detected. Now the working group must determine if the P2F interval is long enough to accommodate an inspection every 3 months and if the net P2F interval is long enough to manage the consequences of failure. Let's look at scenario 1. Let's assume that the asset with the V-belt is taken offline every 6 months. In this scenario, the item can't be monitored at intervals less than the P2F interval because the asset is only offline every 6 months. Therefore, the P2F interval isn't long enough to accommodate the inspection. Now let's look at scenario 2. Let's assume that the asset with the V-belt is shut down every 3 months. In this scenario, the item can be monitored at intervals less than the P2F interval. The RCM working group members identify that the 3 months remaining is long enough to obtain and replace the belt before the asset is scheduled to be restarted. Therefore, in scenario 2, the net P2F interval of 3 months is long enough to manage the consequences of failure. A general rule of thumb is to perform an on-condition task at half the P2F interval, but this is merely a guide. As long as on-condition task intervals are performed at intervals less than the P2F interval, and the net P2F interval leaves enough time to take action, in other words, to manage the consequences of failure, then the on-condition task is considered technically appropriate. The manner in which on-condition task intervals are set is a widely misunderstood concept. When it comes to on-condition maintenance task intervals, there are 4 key things I want you to take away. 1. On-condition maintenance task intervals are not based upon MTBF. 2. On-condition maintenance task intervals are not based upon the useful life of a component. 3. On-condition maintenance task intervals are not based upon the criticality of the failure. 4. On-condition maintenance task intervals are based on the P2F interval. In other words, how quickly something fails once a potential failure condition is detectable. Now let's apply this to failure mode 1A4 in our case study. Plaque and bacteria infiltrate tiny gaps around existing dental work and tiny cracks in teeth due to normal use. Let's read the failure effect. Even with regular brushing and flossing, plaque and bacteria can build up in these areas and lead to decay that may be undetectable by a dentist using a dental explorer, but is detectable via X-ray. Within 18 months of the decay starting, the treatment required for the cavity is a simple filling. However, if the decay goes undetected, it worsens. After approximately 6 more months, the patient may experience sensitivity to hot, cold, or sweet foods due to the exposure of the sensitive dentin. At this stage, the tooth may require a crown rather than a simple filling. If these symptoms are ignored, the decay progresses into the pulp, causing severe pain due to infection and inflammation. The patient may experience difficulty eating, leading to poor nutrition. As the condition worsens, an abscess forms, causing intense pain and swelling. While the pain may subside as the pulp dies, the infection continues to spread, weakening the supporting bone, potentially leading to tooth loss or the need for extraction. Without intervention, the bacteria can spread to surrounding tissues, causing serious infections in the jaw and soft tissues. If the bacteria enters the bloodstream, it can lead to septicemia, a life-threatening condition. In extreme cases, this systemic infection can result in organ failure or death. Back to our case study. We'll focus on the CBM box on the RCM decision diagram. If inspected, is it possible to detect evidence of impending failure? Yes. What is it? In our failure effect, we said that the cavity is detectable via X-ray. What is the P2F interval? Before we can answer that, we need to identify what we define as failure on the P2F curve. Failure on the P2F curve doesn't need to be as failure is defined on the FMEA. In this case, if I'm the patient, I would define failure as simple filling no longer possible. Cavity requires advanced corrective action, for example, a crown. What is the P2F interval? In our failure effect, we said it was 18 months. Is it reasonably consistent? Yes. Is it practical to monitor the item at intervals less than the P2F interval? Yes. Is it long enough to manage the consequences of failure? Yes. If the teeth are x-rayed every 12 months, that leaves enough time to schedule and get the filling done. Does the task reduce the risk of failure to an acceptable level? Yes, it does. So we assign the CBM task, x-ray teeth yearly, fill all detected cavities as required. Remember in part 3 of our case study, I said that failure mode 1A1 couldn't be managed by CBM. It is because there is no potential failure condition. The bacteria is not visible to the naked eye, and pain or other symptoms are not experienced by the patient, and the decay in this early stage may not be detected by the dentist or X-rays. This failure mode is best managed by preventive maintenance. Recall that we assigned the restoration task to floss between all teeth daily to manage this failure mode. Condition-based maintenance is a powerful failure management strategy because it allows impending failure to be identified before the failure occurs, so that proactive action can be taken in enough time to manage the consequences of failure. In other words, maintenance is performed on your terms, not on the equipment's terms. Thank you for joining me for this 4-part RCM case study. If you missed any of the episodes, I will put a link to each one of them below. I'm Nancy Regan. Thank you for watching.